Hi guys, this is the first tutorial video for physics. We're going to go over some basic definitions, some really basic concepts, and a lot of this might seem kind of really intuitive or easy or even redundant. And the reason that is because even if it seems easy or redundant now, as we build up on these concepts, you'll see why we want to do this in a very straightforward and rigorous way. So let's start with some definitions. So the first definition that we have is scalar or vector. And the reason this is important is because a lot of the times when we do physics, direction becomes really important, right? In our everyday life, it doesn't really matter if we say 60 miles an hour, right? By context, we understand what we're talking about. We're going 60 miles an hour on the freeway. It makes no difference if we're going north or south. It's just the speed. And we often use the term speed and velocity interchangeably, but they have a difference in physics. In this case, velocity is what we'd call a vector. A vector has an amount and a direction. So a velocity wouldn't just be 60 miles an hour. It'd be 60 miles an hour north, 60 miles an hour forward or backwards. It can be any sort of direction, so long as it has a direction. And often these are assumed in the problem or they'll be given to you, but you have to be aware of this. And any of these units that are built off of one or another, for example, acceleration. Acceleration is a change in velocity, right? So if velocity is a vector, then acceleration is going to be a vector. When we talk about force, force is based on acceleration. So force is going to be a vector. All of those things have a vector. Scalars are just an amount. Like I said in the beginning, speed would be an example of a scalar. So 60 miles an hour would be just that. Distance, 10 meters, 10 miles, 100 miles, whatever. So as long as it's a distance that is, it doesn't have a direction to it. Mass, 10 kilograms, whatever. Anytime the coefficients are numbers that modify other numbers, we're not going to talk about that in this video. All I really want you to understand at this point in time is that vectors have a direction. It's often something as simple as forwards and backwards or up and down. Doesn't necessarily have to be on the compass, but it can be that as well. And scalars are just an amount that is bigger or smaller, faster, slower, right? That's all that is. So if you think vector, think arrow. And this little squiggly line is to help with the difference between displacement and distance. We often use these terms interchangeably in our casual everyday speak, but in physics, we're almost always talking about displacement. So what's the difference? When we go on a walk and we wander all about the neighborhood or the woods or wherever, what's important to us when we do that is the total amount that we did walking, right? And so that's when we say, oh, I walked, 5 miles, whatever it is. For physics, though, this path that you might end up walking isn't actually important. In fact, in terms of physics, it doesn't really matter. So in those cases, we would have displacement. So it's just the difference between where you started and when you distanced. So this little gap, right? That is going to be your displacement. You can see that these are going to be very, very different. Like I said, in everyday casual conversation, we often use these terms interchangeably because we are going in straight lines or because the distance is what we really want to know. That's the important thing because your legs are getting tired from walking so much, right? That's what we're talking about. But if you think about like things like falling or things that are speeding up or slowing down or like a change in energy levels, it doesn't really necessarily matter all the different processes they go through. It's just the beginning versus the ending. And you'll see problems like that. You'll see a guy started at mile marker 10 and he went to mile marker 20. Are those important? No, it's the difference between those that are important. So that's why we have that. So scalar, it is a vector and an amount. I'm sorry. a velocity is what I was trying to say. A velocity is both an amount and a direction. Speed, just an amount, right? So how do we use these? The units that we're going to be talking about are distance in meters, time is in seconds, and speed is in meters per second. Those are the scientific units. In the United States, we often say miles per hour, and for a lot of, especially the beginning sorts of problems, we kind of use those because they're familiar to people. If I say going 60 miles an hour down the freeway, that's fairly intuitive to people. If I say we're going 30 kilometers a second, or I'm sorry, 30 meters a second, then people kind of wonder, oh, is that fast? Is that slow? What is that, right? And so starting off, we usually use the American units, but over time we kind of transition to the metric systems because the metric systems will tend to make a lot more sense. For example, if I say we are increasing our speed from 10 miles an hour to 20 miles an hour, that is an acceleration, right? And if that happened over 1 second, then it would be 20 miles an hour per second. And if I wanted to calculate the distance that would be, all of a sudden I have 2 time components, and that gets really confusing really fast. And so you want to make sure that all of our units are consistent. You can do it however you want, so long as you're being consistent, the numbers will work out. But just so you know, NASA cratered a multi-million-dollar satellite into the surface of Mars a couple of years ago because they did this and they weren't consistent and they got their units mixed up. So be consistent, use scientific units. It'll make your life just so much easier. So how do we do that? There's a couple of ways. They are all sort of variations on this particular thing. For simple units, you can do these in your head. How many inches are in a foot? There's 12 inches in a foot. So how many inches are there in 3 feet? Well, that's 36. That's easy enough, right? But how many centimeters are in a mile? Or how many meters per second are in miles per hour? Some of these are more complicated and it can be confusing. And so let's start with something that's just very simple. Let's convert inches to feet just so that we can see the process. So there are 12 inches per foot. Okay. And how many feet are we going to do? Let's do 3 feet. Like I said before, let's just make the number out. Here's your process. And I know it sounds like a lot of a process to go through a problem that's just this simple, and it is. But I want to teach you the process using something very simple before I teach it to you using something complex. So let's do 3. That's what we're going to do. So I'm putting out my units there. And this is called the train track method. Other teachers do something similar, but it's all the same. And what we're going to do is we're going to multiply everything across the top and divide everything across the bottom. So multiply in rows, divide in columns. So 3 feet is what we're starting with, and we're going to use our conversion factor. So this is going to be 1 foot per 12 inches. Okay, so we're going to multiply across the top. 3 times 12 is 36. And notice that for my units, we can treat these units a little bit like we would treat math variables, in the sense that if you are dividing by something by itself, in this case, feet by feet, they cancel out. Notice it's just the feet are canceling out. The numbers don't cancel out or anything like that. It's just the feet. And so it's 3 times 12, and this would be inches. And we do this because it really helps us keep track of units, and it helps us know if we're going to multiply or divide, right? So if we wanted to do it the other way around, how many feet is 36 inches? you would do it this way, 36 inches. Kind of got myself a little short there. 36 inches. And now I'm going to take this conversion factor and I'm going to flip it, right? 12 inches. That's because I want my units to cancel out for 1 foot. Okay, my inches cancel out. So 36 times 1 is 36. 36 divided by 12 is 3. So I am left with 3 feet. Okay. As these problems get more complicated, then we can add in more of those. And I'll probably have a separate video showing how you can do those with more complicated ones. I just want to introduce this to you really quick so you can have a way of checking yourself to see if you're multiplying and dividing. I also wanted to show this to you because in the next problem sets, we're going to be talking about how to calculate speed, distance, and time. And it's a very similar process. So let's get rid of this. If I can clear all drawings, that's what I want to do. Okay, so let's say we have a scenario in which Bob is driving at 20 miles per hour for 3 hours. How far did he go? Okay, so that's our question, right? How far did he go? So first thing you do, I know this is a simple problem. I know you can do this in your head, even if you don't even know the equation, you can sort of logically intuit it. But let's go through this process because as these problems get more complex, you're going to want to think a little bit more carefully about them. So first of all, what is this question asking about? Is it asking for time, acceleration, or something else, force? Now, it is asking for distance, right? Or technically displacement. So our equation, we're always going to want an equation, is going to equal distance equals rate times time. Well, velocity times time. I see people using the word rate here a lot, and that's just sort of assumed rate to be velocity, and you can do it that way, but rate can also mean things like the rate of acceleration, things like that. So you don't want to, so the velocity times time. You could also use speed times time here in this case. It's sort of fungible at this point. All right, so I never give my students I never make my students memorize these. I always give them the equation list. And one of the things that is really hard for students is to recognize that this is, even though this is one equation, I can use it a bunch of different ways. The way I've written it out here, I am solving for distance. But if I rearrange this equation, I can solve for velocity or I can solve for time. The temptation is for some students to memorize 3 equations. And that's just not going to work. For one, I'm going to give you a whole list of equations you're going to need to know, and you're not going to be able to memorize them all. You're certainly not going to be able to memorize every iteration of every equation. So figure out your algebra, and we'll go over it in this case. And that's going to make your life just a lot simpler because you're not going to want to memorize things. Just understand the principles involved, and that's how I do it. All right. So you can figure out this in your head. If he drove 20 miles an hour for 3 hours, how far did he go? You went 16 miles, right? So let's write that. Let's do the math. What am I looking for? Drawing. Here's the draw thing. Okay, so we have 20 miles, and I'm just going to abbreviate that MI per hour, and it's 1 hour. And how far did he go? He went for 3 hours. Now, it would seem obvious maybe in this problem, but in other problems, it's not so obvious. So how do I know that I'm supposed to multiply and not divide? Well, you can, again, logically intuit it. Another way to figure this out is, look, if I set up the problem in this way, I know that my hours are going to cancel out. And I'm going to be left with 20 times 3 is going to equal 60. And that is going to equal miles, 60 miles. Okay. Very straightforward. Again, you know, people don't necessarily need to go through this big process to see that, but as the problems get complicated, this will make things easier for you. Let's go ahead and clear this out and try a different one. Clear all the drawings. Okay. So Jill went 20 miles per hour and for 30 miles. Let's make the math easier. Let's see, what do I want here? For 20 miles an hour for 40 miles. How long did it take? Okay, so the question is, what is the question asking for? It is asking for time. You're gonna multiply, you can divide. What are you gonna do, right? Again, set up the problem as before. Your equation is distance is equal to velocity times time. Okay, so I'm going to go ahead and substitute in my numbers for my variables. That's going to be 40 miles. Equals 20 miles per hour. Again, that's 1 hour times time. Okay. So we're just going to divide there. So I'm going to divide this 20 miles per hour. And if you remember your fractions, when you divide by this kind of fraction, the fractions flip. So this is going to be 40 miles divided by 20 miles per hour. Okay. 40 times 1 is 40. 20 times 1 is 20. 40 divided by 20 is going to be 2. My miles cancel out, and I'm left with hours. So it's going to take me 2 hours to do this. Right? Again, this problem, it's probably unnecessary to go through this sort of process, but that's only because it's a simpler problem. As these problems get more complicated, you're going to need a system like that. So that's how you do this sort of thing. Last thing on this particular video is, let's do a gut check. Does it make sense that if we're going 20 miles an hour for 40 miles, that it should take about 2 hours? Yeah. If you somehow got this mixed up for whatever reason, and you say, let's say we put this into our calculator wrong. Let's say we put it into our calculator 20 divided by 40. I've seen students do that. You would get half an hour, right? Does it make sense that you would go 40 miles in 20 miles an hour and do that in half an hour? No, it doesn't. So kind of do those gut checks. If you get up something different than what your gut sort of kind of tells you is right, it may be that your gut is wrong and your math is right, or something could have happened. So you just want to double check that really quick. All right, that is it for this particular video. I hope you found this enlightening, and if there are any questions or comments, go ahead and let me know.